Good morning, everyone. And today we will start with another session on our course on line commutated and PWM rectifiers. And today's discussion will be on a new topic, which is PFC boost rectifier. Here we will cover the basic operation and the steady state analysis of this PFC boost rectifier. So if we see the course structure and the content, we are now um, basically in this week here, single phase AC-DC converter. So we have already covered these uh, subjects. And here in the PFC boost rectifier, we will talk about the power circuit and the steady state analysis and how we achieve unity power factor. And also we will briefly touch upon the design of the L and C, which are very crucial components in this PFC boost rectifier. We will all discuss today. Okay, now, so yeah, this is our content. So let us first see what is the broad application area of PFC circuits. Why are we studying uh, this PFC? We have already seen some of the PFC or power factor improvement circuits before in this course. We have seen the three-phase PWM rectifier, and we had done an extensive analysis for the for with a DQ analysis of this kind of three-phase voltage source converters, which are interfaced with the grid. Now, um, the PFC circuits, especially, okay, is the application area is slightly different. And this application is uh, basically related to a little bit lower power rating. Lower means generally the PFC circuits are from like few tens of watts to about 1 kilowatt. So if you see here, usually the power range is like this 1 kilowatt is not a very strict limit. Okay, so it can go beyond 1 kilowatt. In fact, if we say the modern generation PFC rectifiers are coming more than 1 kilowatt also with silicon carbide, I mean better quality of devices. But generally these PFC circuits are uh, like in this power range. Okay, whereas three-phase VSCs, which we had talked earlier, they can go like many hundreds of kilowatts. Okay, now with this less than 1 kilowatt, like 500 watt, 600 watt, or even 100 watt. Okay, where do we find the application, and where do we see them actually? So this kind of PFC circuits are widely used in consumer electronics. Okay, where suppose if you have a laptop from which I am recording my slides, so this laptop also has a power supply. If you see your laptop, it also has a power supply, and that power supply will have some form of a PFC circuit inside. The Usually the power range of this kind of laptop power supplies are less than 100 watt, typically 70, 60, 70 watts, but less than 100 watt usually. And the voltage output of these laptops are around 20 volts. Okay, and um, these are uh, these kind of power supplies are also available. Like if you see your TV power supply and several household electronics, okay, there also you will see this kind of power supplies, or even in lighting. Okay, this lighting is also very important application of these PFC circuits. So what do we need here? We want a stable DC output, okay, which is obtained from the AC grid. Okay, so this is the input output input output characteristics of this kind of PFC circuits. And the of course, when we connect it to the AC grid, as I have already mentioned, we have to be very careful in what is the harmonic distortion or the THD. We have to maintain that one. And in all these PFC circuits, we have to keep the power factor at the input. If you see here, the power factor should be very close to 1, close to 1, very close to 1. Okay. Uh, Typically, the power factor of these kind of circuits are like 0.98 to 1. Okay, it's like that. And so this is very important even for consumer electronics. In earlier days, say like 25, 30 years back, this kind of for a small consumer electronics which we use in our daily lives, these kind of these kind of power supplies were not so stringent in terms of the THD. So here we have to important like these two things, THD and the power factor. These two are important things we have to remember. So the 30 years back, this THD and power factor was not so important. Power factor was important, but THD was not so very strict. Okay, 30, 40 years back. But now, with the rapid growth of many electronic items that we use in our daily lives, almost all of them will come with this kind of a stringent requirement. So if you are a designer for this kind of power supply, you must maintain certain standards like IEEE 519 or IC 610, and you must adhere to these standards, okay, which is very important. And also in future, we also expect that the power consumption of these kind of consumer electronics will grow. Okay, we will have more gadgets in our daily lives. And so these things will become more and more profound. And that's why it is important to maintain the quality of the current drawn. Okay. But these PFC circuits are not only limited to consumer electronics. Okay, it is also very much used commercially. Okay, where do we use it in commercially? We use it in, say, the telecom power supplies. Okay, so if you see in many places, you see telecom towers and then telecom power supplies. Then we use it in servers, data centers, lighting, commercial lighting. Okay, very much in use. And battery chargers. See, suppose in India, we see now a lot of two-wheelers and three-wheelers, electric vehicles, two-wheelers and three-wheelers. All of them have batteries, and usually we um, charge them overnight from the grid. Okay, and this kind of PFC circuits will be used in these kind of battery chargers. As I told you, the power range is in this range, roughly, not very strict about it, but roughly this range. But mostly the voltage, okay, mostly we use the single phase voltage because our consumer electronics, all our household electronics is single phase. Mostly we will use single phase. So single phase, we in India, we have 230-volt 50 hertz system, but in some other countries like USA, we have 120-volt and 60 hertz. And one of the things that as a design engineer or as a product builder, you have to remember that sometimes we build PFC circuits which can be sold anywhere in the world. Okay, so which means that in that case, you have to design for both the voltage and the frequency level. Frequency is not so stringent requirement because you will see how we will work it. Frequency is not a challenge, but the voltage 120 and 230 volt, this voltage has some challenges in the design of the PFC circuit. Okay, if you are specific for a particular country, then the design becomes much easier. But if you want to build a universal power supply, which can work at both 120 and 230 volt, in that case, your design will become more challenging. And we will see how this challenge comes in the as we go progress on the slides. Of course, for higher power, we have the three-phase circuits. We also have either we can use three-phase VSCs, but we can also have three-phase PFCs. But in this course, we will primarily focus on the single-phase supply. Okay. Now, let us just quickly see what we have already know. We already know in the course that when we want to convert, okay, the from AC to DC, as you can see here, we have the AC this side and we have the DC on this side. Okay, this is where the DC comes, and we know it very well from our this thing. So the easiest way to do this AC to DC conversion is to use a diode bridge rectifier, okay, which has been there for a long, long time, very stable, very robust product. And we will also continue to use this diode bridge rectifier, but we will use some switches along with the diode bridge rectifier. Okay, it's a simple circuit. The first circuit here is good. Just to recap, we have already done this, but the DBR is a simple circuit, but the problem is this output here is, the output here is something like this, okay, oscillating. So the output voltage is not stiff. And in order to make the output voltage stiff, that is what we want to do. We want to like this, something like this. We use a capacitor here. Okay, we have covered this previously. Um, Now, when we use the capacitor, there is one problem, as we have also seen before. Just I'm recapping all the previous thing. The 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 output voltage, as you can see here, this is the V0 voltage here. Okay, this V0 voltage is basically like a DC. Okay, it may have a small ripple, but it is basically DC here from the input AC grid, right? But the problem is, one of the biggest problem is that if you see the grid current, okay, the grid current is coming from here, and this current is very much peaky in nature. Okay, this is in peaky because it will only be conducted when the AC, instantaneous AC voltage is more than the instantaneous output voltage. Okay, and we have discussed this in lecture 5, and the profile of the source current is not at all sinusoidal, and this is where the it will not follow. So the grid standards are violated. If you look into the IG current, this IG current, this current here violates the grid standards, which so you cannot sell this in the market. Okay. So what do we do? Now, when we want to produce a rectifier, okay, suppose we want to produce the ideal rectifier, right? So then what, how do we vision it? Okay. The way we look at it is that we have the AC source here, okay, and the AC source, which is the grid here, and this is the whole converter. Okay, this is where the converter comes. So just yeah. So this is where the converter comes, right? Now, seeing from the input of the converter, what do we see this one? We want to see an ideal rectifier. Okay. What does that ideal rectifier means? Because we want a unity power factor. Okay. So if we want to operate at unity power factor, then this entire converter can be represented by an equivalent resistance, right? This resistance, which we called as RE, okay, is the emulated resistance. Why it is an emulated resistance? Because it may not be physically a resistor, okay, but we want to emulate this resistance, okay, by doing internal switching of the converter and doing whatever, all sorts of things inside the converter. What we want is that the current here, the grid current, okay, the AC current here, AC, this current should be exactly proportional to the applied voltage, okay, and divided by this resistance RE, okay. So therefore, since VAC is a sinusoidal voltage, the grid voltage is sinusoidal, 120 volt or 230 volt, then this RE, the grid current should be perfectly sinusoidal. If it is perfectly sinusoidal, then we actually have a harmonic distortion which is zero. And we have the ideal condition, and we have a perfect sine wave input current. So, and also since this is unity power factor, so the current and the voltage are always in phase, and therefore the relation here, relationship one here, is perfectly valid. Okay. And one more important is VAC is a sinusoidal quantity and it is continuous in nature. So therefore IAC should also be sinusoidal and continuous. Okay. So therefore we can say always that if this is the VAC, IAC is nothing but a scaled version of the voltage. Okay. This is what we can say. So this is like IAC and this is the VAC. Okay, so this is what we want. Now, this RE here, how we are representing the RE, the RE is not necessarily a physical resistor. That's what I want to emphasize here, that it may be an emulated resistance. So the entire converter, we may switch in such a way that from the grid point of view, the grid sees as an equivalent emulated resistance where the voltage and the current is perfectly in phase, sinusoidal and continuous. Okay. Now, the question here now is how can we force IAC to be sinusoidal and continuous? Now, one technique which is very useful in this case, and that is what we are going to discuss here, is to use a DC-DC converter after the DBR. Okay. So this, the other technique that we had earlier seen was to force this current through the DQ analysis. We have seen that is one method of doing it. For single phase application, it may be more advantageous actually to use at low power level to use this type of a circuit with a DBR and a DC-DC converter. Okay. So what does this do? Okay, so you can see that this, so we will explain what is this one, but this DC-DC converter here, you can see that the output, so let us see the input and output. The input to this DC-DC converter is a voltage which is something like this, okay, rectified voltage, whereas the output voltage, as we know, we want a DC output. So this is the V0, V output. Okay. So here is the V output, and here is the grid voltage and the rectified voltage. Okay, this is the VG. Okay, and here is the VG voltage. Fine. So the VG voltage is a rectified AC voltage, and so we can actually have a boost converter. Other types of converters are also possible. Okay, like Chuk converter, Sepik converter, etc. But boost converter, but these are higher order converters, like fourth order. Chuk converter is a fourth order converter. So we usually use the simplest converter, which is the boost converter, and boost converter has certain advantages, okay, which we will use as, and you will understand what is the advantage that we are going to get. Okay, now um, one thing that is important is that unlike, so you must have studied traditional DC-DC converters like buck converter and boost converter. One thing that you should remember is that um, in a traditional DC-DC converter, the input voltage and the output voltage are both DC, okay, and they do not Of course, they can fluctuate a little bit, but they do not fluctuate continuously in a very rapid fashion, okay, at steady state. So, but in this case of DC-DC converter, as you can understand, this DC-DC converter here is already we are seeing a case where the input voltage here, this input voltage is already a rectified voltage. Okay, so this voltage is already rectified. So which means the voltage is continuously changing, whereas this output voltage here is fixed. Okay, so we are already asking this DC-DC converter to work in a situation with a variable duty ratio. Okay, the duty ratio of the DC-DC converter is continuously changing with time because the input voltage is continuously changing. Okay, um, and this is one thing that we must. So therefore, we need actually also a closed loop controller. Okay, the because we are going to manipulate the duty ratio continuously. Okay, we are going to change the duty ratio continuously so that in the presence of this varying input voltage, we get a fixed DC output voltage, right? Uh, Now, one of the things is you must remember that the AC voltage, okay, this AC voltage which comes from the grid, do not expect that this AC voltage is always fixed at a particular value. Okay, so what can happen in many places? Okay, suppose we have a weak grid or we have a yeah. So even if the nominal voltage is 230 volt AC, this voltage can actually go up or down. Okay, for example, you may face a situation where at night the voltage has gone to 235 volt, whereas on at the daytime this voltage is going to 220 volt. Okay, so it is fluctuating, right? So you can see that such a situation is very much expected in from the grid point of view, right? But suppose you are giving to a telecom power supply, you must maintain a 48 volt output, no matter if the grid voltage is fluctuating. So this is also the reason why we need a controller. Okay, and the controller will understand uh, the grid voltage fluctuation and will accordingly change the duty ratio. Okay. Uh, Also remember that the power drawn, this RL here is not constant. Okay, we must understand this one, that this RL is not constant. Okay, the RL can actually vary. Why it can vary? For example, you are putting it into a server power supply. Okay, 48 volt server power supply. And in that server, sometimes the processing is high and sometimes the processing is low. And so for example, at daytime, the server is heavily loaded. At night time, the server is not so heavily loaded. So the power consumed by the server is varying from day to night. Okay, so therefore this RL, the load which is seen by this power supply, that will also vary, right? So RL is not constant. The input AC voltage is also not constant. So therefore, we definitely need a closed loop control. Okay, because whenever we are working, we have to ensure that these are the two most important things which we maintain: the THD and the power factor. Okay, these are the two most important things that we have to maintain from the input perspective, from the grid perspective. Of course, along with this, we have to maintain the output voltage as constant. Definitely, this is also very, very important. But from the input point of view, these are important. And from the output point of view, V0 has to be maintained. Okay. So we need a closed loop control. Now let us understand a little bit about the boost converter. Okay, now you may also ask that why did we choose the boost converter and why not a buck converter? Okay, one of the okay, we will come to that. Okay, but one of the reasons of using a boost converter is that the boost converter has the input current which is continuous. Okay, I will come to this a little bit later, but the buck converter is not like that. The buck converter or a buck boost converter has the input current taken from the source is discontinuous current, and that actually creates more challenges when we want to ensure a power factor correction operation. Okay, so boost converter is an ideal choice, right? And as you know, one of the important criteria of the boost converter is that the input voltage, okay, the output voltage, this is the output voltage here. This output voltage V, okay, should be always greater than the input voltage. In this case, the input voltage is VGT. Okay. So in a boost converter, V should be greater than VGT all the time. Okay, VGT, remember the VGT voltage is this voltage here. Okay, what is this voltage? How did I get this voltage? Because here is the AC voltage. So you can see here, this is the AC VAC voltage, and then I have rectified it. After rectification, I get this voltage VGT, okay, with a peak magnitude of VM. Okay, so we can represent like VM sine omega. So the important thing here is that this capital V, the output voltage, because we are boosting the voltage, right? So this is a boost converter. So output voltage, the output voltage should be always more than the input voltage. So the output voltage you can see here will be always like this. Okay, this is the capital V. Okay, this is the output voltage. The output voltage should be more than the instantaneous input voltage all the time. That is where the boost converter comes into picture. Okay, so now with that understanding in our mind, what we can see here is like uh, what we can see here is that the the input voltage VAC is suppose, so we can do a small like we can start writing the expressions. Okay, so the input voltage of the rectifier is VAC. So this is VM sine omega t, which is shown here, uh, and the rectifier output voltage, which is VGT, and we have already shown is VM mod of sine omega t, right? Because we have rectified it. The converter output voltage can be considered. So this is very common because we have put a capacitor here, and that capacitor ensures that, of course, the output voltage is more or less constant. Okay, there may be a small ripple, but this ripple is designed in such, the capacitor is designed in such a way that this ripple is more or less like 1% or even less than 1%. Okay, the ripple voltage. So therefore, the output voltage is almost constant. Okay, we can assume this very without much problem, without much difficulty. VT is constant. Okay, the output voltage. So now then the what is the converter duty ratio? Okay, so the converter duty ratio dt. Okay, so we are using this converter here, this DC-DC converter. The converter duty ratio is VT divided by VGT. Okay, right? Which will change. So this is V by VM sine omega t. Okay, so as I told you, in a boost converter, this is the capital V, this is the voltage here, capital V, and so the controller should vary the duty ratio between infinity at the zero voltage. So when this voltage is uh, close to zero, okay, near to the zero, the duty ratio okay, should be very, very high, right? Because we are basically boosting a lot of voltage when the input voltage is small. On the other hand, when the VG voltage is at the peak, okay, which is here, okay, at the peak, then we have a minimum duty ratio at the peak of the AC voltage, okay. So this is how the minimum value of the duty ratio is V by Vm, right? And of course, if we can ensure this one, okay, with this, we will see that the DC-DC converter, because we have a closed loop control here, we will ensure that this current, okay, the current which is flowing through here, IG, okay, this current IG is like a rectified sine wave. Okay, it will be very close to this rectified sine wave. I will show you later the uh, waveforms, but ideally this IGT should be like this way. Okay, in the waveform. Okay, if we can ensure that this is happening, then of course IAC. Okay, this waveform here IAC will become like this. Okay. Um, Number one is it will become sinusoidal because the DC-DC converter, we are switching it in such a way when we are forcing this IGT to be sinusoidal. Okay, that we will do. But the other thing that we will also do is to make sure that this voltage and this current are at unity power factor. Okay, so they are exactly in phase. So therefore, of course, we assume that the diodes are all ideal, which is true in most of power electronics. The diodes are very close to ideal devices. Okay, so therefore, this is the IGT and this is the IAC, and therefore we will run the DC-DC converter with certain value of duty, continuously varying duty, which is shown here. Okay, continuously varying duty, so that the output and input voltage are maintained along with the input currents to be sinusoidal, continuous, in phase. So here you can see what this voltage conversion ratio, as I was telling you, the because boost converter, you know, the duty ratio of boost converter, just for your understanding, V0 by V in is equal to 1 by 1 minus D. This is the voltage gain expression of a boost converter. In this case, the D is varying. As I told you, the D is varying. So this D is no longer a fixed value, but this D is now a function of time. Okay, fine. So ideally, a boost converter actually can vary the output or can vary the voltage gain from 1 to infinity, okay, corresponding to D equal to 0 to 1, okay, D equal to 0 to 1. You can theoretically, you can have the gain, voltage gain from 1 to infinity. Okay, of course, you will not have infinite voltage gain. That is not possible. But ideally, if you see, so a boost converter is a preferred choice. Okay. Now, as I told you, the boost converter has input current continuous. Okay. If you can recall how a boost converter looks like, I will show you in the next slide itself that this is the switch and this is the diode, and this is how the boost converter looks like. Okay. If you recall your DC-DC converter knowledge, this is how a boost converter looks like. So that this current here, okay, which is coming from the source, this current is always continuous, okay, whether the switch is on or the diode is on, right? But this is not the case if you say take a buck converter. Okay, suppose you take a buck converter, the buck converter looks like this. Okay, and here you can see that when the switch is on, the source current, okay, when the switch is on, the source current is flowing, but when the switch is off, the source current is off. So which means the source current is discontinuous, right? This discontinuous, now imagine this discontinuous current coming here, okay, on the input, okay. Then this current, discontinuous current, which you are seeing here, will get reflected here, okay, on the source current, on the AC side current. So it will create problem for us, right? So we do not want, and there will, so this discontinuous current, we will need additional filters at the input of this AC source so as to make the grid current look continuous, ripple free like that. Okay. So it will become a more complicated and difficult design to undertake. Okay. And that is one of the reasons why we do not use a buck converter usually. It is possible to use a buck converter. I'm not saying it is not possible. It is possible to use a buck converter, but we need some additional component, filters, or some additional logic somewhere that will make this input current continuous, ripple free. Okay. Compared to that, the boost converter is a much better solution. Okay. So we will actually, this DC-DC converter, what we have, we will stick to this boost converter. Okay. Now, Chook, Sepik, etc., these fourth order converters can also be used, but boost converter being a second order system is simplest to control. Okay, Chook, Sepik converters have more number of inductors and capacitors. Okay, so the PFC boost converter has been there for the last 30 years. It is very popular, commercially available, and very well established technology. Okay, so people have chosen this converter over other converters. Okay, so here you can see the circuit, right? Uh, so what do we have here? So this, now we are looking into what is inside this DC-DC converter, and you can see here there is this inductor, there is this switch. Usually we use MOSFET here. We do not use IGBT because these kind of boost converters can easily switch between say 50 kilohertz to 200, 300 kilohertz very easily. Okay. So we will have to use most likely MOSFETs here, okay? Depending on the power rating and the maturity of the technology and what is the cost that we can incur, what is the power rating, we may use a silicon MOSFET or we may use a silicon carbide MOSFET, okay? Both are possible. Then here we have this inductor here, we have this switch here, and we also have the diode. Okay, and we have a controller. The controller checks the generates the duty which is given to the gate driver here, and the gate driver generates the pulses. Okay, gate drivers is here. Okay. Um, okay, so let us, so this is the whole circuit which we are going to analyze. Okay, now let us see how we can proceed with the analysis. Before we go into the detailed analysis of the boost converter, certain important factors we have to understand is the overall, what is the role of these capacitors like that. Okay. Um, so here, suppose we, in this boost converter, suppose we assume that the stored energy in this lossless boost converter is negligible, right? So the instantaneous output power in that case will be equal to the instantaneous output power. Okay, instant input and output power. So you see here we have this as the instantaneous input power coming. Okay, and this is the output power which is going. Fine. So the so therefore we see that of course the output, instantaneous output power is Vt into It, and the uh, this thing, the input power is Vg into Igt. Okay. Now Assume that Vt is almost equal to a constant voltage, okay, capital V. And so the IGT here will be equal to, we know that we want the IG current, this IAC current, okay, to be perfectly a sine wave, right? So which means that IGT, okay, IGT, as we have seen in the waveforms before, IGT is an exact replica of the rectified voltage divided by the emulated resistance, and emulated resistance is the resistance seen from this terminal. Okay. So RE is the emulated resistance. IGT is VGT by RE, right? Now, let us see what are the input and output currents. Okay. So now here the IT, we can say because it is, we can substitute in the previous equation. Okay, here IGT is VGT by RE, and so we substitute in this equation of VT into IT equal to VGT into IGT. Substitute there, and then we get an expression of IT. Okay, this current here, IT. Okay. Now, in this current, what we see here, it is VGT square, VG square T divided by VRE. Now, what is the expression of VGT? You can see here, if you substitute VGT, VGT is, as I told you, Vm into mod of sine omega t. VGT here, this is the voltage, this is this voltage here, VGT. Okay. So this is Vm sine omega. So therefore, the IT, okay, the IT here, okay, this IT will be equal to, just putting it back, will be equal to Vm squared by 2 VRE into Vm squared by VRE into sine square omega t, right? And which will be equal to 1 minus cos 2 omega t. So what it shows is that this current which is flowing here, okay, this current before the capacitor, this current contains a DC component. The DC component is this one, okay, and a second harmonic component, and the second harmonic component is this one, okay, Vm squared into 2 VRE into cos 2 omega t. So this current IT has both these components. Okay. Now, as we know that a capacitor, okay, a capacitor is basically has infinite impedance at DC, because the impedance of the capacitor is 1 by omega c, and at omega equal to 1 by at omega equal to 0, the capacitance has infinite impedance. So therefore, ideally, all the so no DC can flow through the capacitor, and so all the DC will flow through the load. Okay, whereas ideally, the entire second harmonic, okay, the second harmonic should flow through the capacitor, right? And we do not want the second harmonic to flow on the load, right? Because if we have a second harmonic flowing through the load, then we will have an additional second harmonic ripple, which we don't want. So we want the second harmonic current to flow entirely through the capacitor, whereas the entire DC component of IT flow through the load. Okay. Uh, So therefore, we can also say that the IT has two components, I average and I harmonic second, which are given by these two expressions here. We should also note that the average power, okay, what are the average powers? Okay, we'll talk about instantaneous power a little bit later, but if you just note the average power, what is the average load power? The load voltage is constant, capital V, and the um, current, okay, the DC component of the current, okay, this current, the DC component comes here, Okay, IT, the DC component of current. So this is V into I average. Okay, right? So this is equal to Vm squared by 2 V RD. And so when you substitute this and do, you see that P load is equal to Vm squared by 2 RD, and Vm squared by 2 because we are using a sinusoidal AC voltage source. So therefore, this is equal to VAC RMS squared divided by RE, right? And this means that this voltage is, this power is equal to P in, right? Because this is an emulated resistance, right? Seen from the grid. And so this input power is nothing but V RMS square, VAC square divided by RE, right? So at steady state, okay, P load and P in must be equal, and this should be happening. And we can see that this is happening in this circuit, okay? The average powers at the input and the output are equal. Um, if we do not have this condition satisfied, okay, for example, you have P load less than P in, okay? So what will happen is, suppose you have P load less than P in, then what will happen? The capacitor voltage will start to rise, okay? Because it will absorb more energy as compared to what it can deliver, okay? So the energy content will increase in the capacitor, and it will get manifested in the form of increased voltage, because half CV squared is the energy content of the capacitor. So it will get manifested in the form of an increasing voltage. So therefore, uh, this condition of P load equal to P in must be valid at steady state. Then the converter will operate steadily. Okay. But what now happens with the instantaneous input and output powers? Okay. So the previously we said about the average input and output powers. What about the instantaneous powers? So instantaneous input power P in, okay, is nothing but VAC into IAC T. Okay, it's function of T. So which if you again substitute and just do the calculations, you'll get something like this. Okay, Vm square by RE to 1 minus cos 2 omega t. This is known to us from basic circuit theory that the for an AC input voltage, the power which is drawn, suppose this is the input voltage and this is the current, right? VAC into IAC, this is the input voltage and current. Then the power, is something like this. Okay, this is the power. It is oscillates at twice the frequency. Okay, so we can see that the input power, okay, this is the input power, okay. The input power has this average value, which is Vm square by 2RE. This is constant here, okay. So this is constant, but the input power has a fluctuating component. So which means the input power is not constant, okay. This you cannot stop, okay. Nobody can stop it, right? Because we have made voltage, AC voltage and AC current to be sinusoidal, and from fundamental principles, the input power will always have this fluctuating component. On the other hand, if you see the output power, okay, P out T, for a DC load, this output power will be constant, right? Because we have seen that the voltage and the currents, we make it constant. So we want an output power to be constant, right? So the input power is fluctuating, but the output power is constant. Hence, we need some form of energy storage, L and C, inside the converter. Okay, this is another way of analyzing the circuit. Okay, it is not necessary, but it gives you another perspective from the power equivalence. Okay, just wanted to discuss this with you. Okay, Now let us go into the detailed operation of the converter during each switching cycle. Okay, so here is our converter, and which is now drawn in a very standard format, and we will analyze the operation of this converter. Now, when we analyze the operation of the converter, we have to do it in two stages or in two steps. Okay. One thing is we have to understand that the diode bridge rectifier basically has two switching states. What are these switching states? The first switching, so in the positive AC half cycle, D1 and D4 are conducting. Whereas on the negative half cycle, D3 and D2 are conducting. So that is what makes this output voltage something like this. Okay, right? And but this change is happening at the AC line frequency, like 50 hertz or 60 hertz, right? So therefore, this time duration here is like this time duration is 1 by 50. This time duration is 1 by 50, which is equal to 20 milliseconds, right? So therefore, this is equal to 10 milliseconds, half cycle. So this changeover is happening in the millisecond range, okay? And the diode bridge rectifiers are always alternating between this positive AC cycle and the negative AC cycle, right? And yeah, this is happening at millisecond range. But on the other hand, if you see about from the boost converter perspective, the boost converter also has two switching states, right? And you can understand it is like a traditional boost converter. Uh, we have two switching states, one when the switch is on and one when the diode is on. If the diode is on, if the switch is on, then the inductor charges. And when the diode is on, the inductor discharges. Okay, so these are the two complementary switching states. Uh, so the boost converter also has two switching states. Okay, but the boost converter works at a much higher switching frequency. Okay, um, uh, generally, as I told you, it can work like between 20 to 100 kilohertz. Okay, now this means that the boost converter is operating at a much faster rate, or the switches in the boost converter are operating at a much faster rate as compared to the diode bridge rectifiers. Okay, so uh, we can have actually four possibilities. Okay, in each for to analyze in order to analyze the converter, we have now four possibilities. What are these possibilities? First is the positive AC cycle, and in the positive AC cycles, which means, and so this is the number one condition, okay, positive AC cycle, and the switch PFC, SWPFC is on. So this is the number one condition. These two are happening, okay. So the in the positive AC cycle, but because remember, positive AC cycle means this is happening in the first 10 milliseconds, right, from the previous slide. So in this condition is happening, so that switch may be turned on. Whereas now take the second condition, the same positive AC cycle, but I have now turned off SWPFC and turned on DPFC. Okay, so therefore SWPFC is off and DPFC on. So this condition will happen. So the same D1 and D4 is conducting AC cycle positive side, but now the boost converter, the diode is conducting. So this condition we are saying condition number 2. Okay. So this will alternate 1 and 2. These two states will alternate as the boost converter switch and diode, they are switching. Remember, the boost converter is switching at this frequency much faster than the diode bridge rectifier. Now, next, what will happen? Next, we take this condition when the negative AC cycle is happening. This condition is shown here where D3 and D2 are conducting. Now, in this condition, during this negative AC cycle, what we will see is that again, the boost converter switch or the diode, meaning DSW PFC and DPFC, they will be conducting. It is possible. So therefore, under this condition, if the switch is on, then we say that this is the third condition. Okay. And then we have the fourth condition where in negative of the AC cycle, SWPFC is off and DPFC is on. So then we have this condition. Okay. Right. So we have all these four switching states possible in this converter. Right. And we can analyze the first one, and then we will see the first and second one, and then we will see very easily the third and fourth, because third and fourth is like a replica of the first and second. We'll see this one. Okay, let us go back to the slides. Okay, now uh, before I show you the analysis of this one, I just wanted to show you the waveforms. Okay, now you see here, as I told you, the operation of the converter, as I told you, uh, if you see this waveform first and then start analyzing, then it will be easier for you to visualize. Okay, so you see here that, as I told you, the IG, this is the current. Okay, IG current which is flowing. Okay, this current is flowing here, IG equal to IL. Okay, the inductor current as well as the rectified grid current. So this current ideally was something like this one. Okay, but now here you see that we have actually a band. Okay, how this band is coming, we will tell you now. But remember, uh, if we follow this current, we can also find out what is ID1, D4 and ID2, D3, because here you can see the D1 and D4 are conducting. So that is why I have got D1, D4. But here D2 and D3 are conducting. So this current is replicated from here. And of course, the AC grid current, you can immediately tell that the AC grid current will be, if I draw the AC grid current at the top, it will be something like this. Okay, but here you can see we have drawn a band here. Okay, you can see here there is a it's not a straight line. Okay, there's a band. Okay, there's a small band of current. The question is, how is this coming, this band of current? This band of current is coming because of the operation of the boost converter. So if you zoom in into this band, okay, what will you see? Okay, you will see the inductor current basically. Hmm? So this is the zoomed portion, okay, and this zoomed portion are shown here. Okay, so in that zoomed portion, you can see that the current is basically rising and falling, okay, depending on when the switch and the diodes are conducting. Okay, uh, remember what we are seeing here is that this distance, this time duration here is 10 milliseconds. Okay, remember this is 10 millisecond. The zoomed region. Okay, so in the zoomed region, this can be, suppose this boost converter is running at 100 kilohertz. Okay, so which means that the time period is 1 by 100 kilohertz, which is 0.1, which is 10 microseconds. Okay, so therefore this one can be 10 microseconds. So the zoomed version is 10 microsecond. Okay, so this is what you have to carefully observe. The the zoomed version here, in that 10 microsecond, the boost, the SWPFC, the MOSFET and the diodes are conducting one by one alternatively. So when the MOSFET is conducting, as you can see, the current is rising. Okay, this is where the current is rising, and you can see ISWPFC, the current through the MOSFET, that is rising. Okay, here. Okay, and then the diode current is flowing. Right, the diode current is flowing. Again, it is rising and falling like that. In that small window, where the total switching period of this MOSFET and diode is 10 microseconds. Okay, so this is how it will look like. This is how you will visualize it, or it will appear on you. Now, why is there a band? The band is this band here. You can see this band here is this band basically. This is the band of the current, right? This band is this band of current here. This small band of current which we are seeing here is nothing but this thing. Okay, and why is this band happening? This band is happening. This has to happen because it is a boost converter, and so the inductor current will rise and fall, right? And so that is what this band is called. That is how this band is caused, right? So therefore, you can understand that the in the entire AC cycle, the current is almost sinusoidal, but it is not perfectly sinusoidal, right? So it will start from zero here. Okay, so it will start from zero. It is almost sine wave, but with a band. Okay, with a band, here. This band is happening because the boost converter is switching. In many cases, this is quite acceptable. Now we have to see whether this is acceptable to the grid or not. Okay, so the THD, if this band can, if this band is okay, and we say that the THD is not bad with this kind of a band of current, then we are saying we are fine. Okay, because one thing that you have to observe is we can ensure a unity power factor operation. Okay, because the current is starting from zero, and we can synchronize it with the input voltage. Of course, it has a band of current, but the band can be very limited. Okay, and so we will be able to make sure that this current IAC here, which is flowing, which is the replica of this IG with a negative sign also. Okay, the IAC is, yeah, the IAC is this current, but of course there is a small band here, okay, which is coming from the switching of the boost converter. If we say that this is okay, fine, this is at unity power factor, and the band is okay, the harmonic total THD, the total harmonic distortion is fine, acceptable to us, it is less than 5%, then we say, yes, this converter can work nicely. Okay, so this is what it happens, right? So yeah, this is, so you can see how we are actually dealing with two uh, different circuits, I mean, same circuit, but two different time constants in the circuit. One is on the diode bridge rectifier, which is working at 10 millisecond thing, but the other one is operating much faster, say, suppose like at 10 microseconds. Okay, so Yeah, this is what I have already explained, like zooming into the switching cycle, the inductor current ripple can be seen. Okay, here is this inductor current. You can see the inductor current is rising and falling. So this is what is shown. The inductor current charges when the switch is on. The switch current is also shown. You can see here ISW and ID. Okay, fine. Now let us go and write a few equations based on this understanding and how the switch, so we can analyze the switching state. Okay.